Thank you, Dr. Chang, for the introduction. Hi, everyone. I'm very glad to be here to speak to you about ventilation and the role it plays in the midst of the COVID-19 pandemic. So to start off, I would like to thank the Department of Health for giving me the opportunity to deliver a presentation in this very meaningful webinar on prevention of COVID-19. I will begin this presentation by giving a brief overview of EMSD and the role that we play in tackling COVID-19. EMSD is an engineering department of the government of the Hong Kong SAR. Apart from enforcement of many of the electrical and mechanical safety regulations in Hong Kong, the EMSD also acts as the technical advisor and engineering services provider for the government and various autonomous bodies like the Airport Authority and Hospital Authority. The focus of our services is to provide operation and maintenance of the electrical, mechanical, electronics, building services systems, and equipment at major venues such as government office buildings, hospitals and clinics, airport, ferry terminals, public markets, and civic venues. For many of the public venues that you might come across on a daily basis, the E&M engineering systems are likely to be maintained by us. To support the government's pro-innovation procurement policy, EMSD, thanks. So the PowerPoint seems hang. Okay, look, all right, sorry. Okay, to support the government's pro-innovation procurement policy, EMSD has taken on the role of innovation facilitator for the government departments. In the wake of the epidemic, we have proactively recommended applications of innovation and technology solutions to help tackle the COVID-19. For this purpose, EMSD launched the E&M Inno Portal website, which lists the service wishes of various government departments and public organizations, and invites innovation and technology sector, including startups and universities, to propose relevant innovation and technology solutions for matching. We also have a special section on anti-epidemic innovation and technology applications. Everyone is welcome to submit their wishes and solutions. So that's the end of our advertisement. So now let us get back to the topic of our presentation. And what is ventilation? The word ventilation originated from the Latin word ventus, which means wind. Later, the word ventilation means replacing air in an enclosed space with new and clean air. There are generally two types of ventilation, natural and mechanical. There is also a third type, which is a hybrid of the two. Natural ventilation means air from outdoor is being forced indoor due to the natural forces such as winds. And on the other hand, mechanical ventilation, as its name suggests, means air from outdoor is being forced indoor by mechanical fans, by air ducts, and or extracted from indoor to outdoor by exhaust fans. The table now shown on the slides indicates the pros and cons of each type of ventilation. As one can imagine, natural ventilation is free of charge and capable of achieving high ventilation rates. Since it does not need electricity to operate fans as compared to mechanical ventilation, energy consumption is relatively lower, or even zero. On the cons side, natural ventilation depends heavily on the weather condition and wind direction. In humid places like Hong Kong, we rarely see buildings that uses natural ventilation. Mechanical ventilation is much more reliable in delivering the required airflow rate regardless of the ambient conditions. Also, air purification systems can be installed in ductworks to control the indoor air quality, and airflow path can be controlled by designing the system with high and low pressure zones. The drawback of mechanical ventilation is that it has high initial installation costs, the fans consume electricity, the equipment and air ductwork needs spaces and requires proper maintenance. Today's presentation will mainly focus on mechanical ventilation, which can be controlled by humans. So before going forward, I would like to share with you some of the common terminology found in discussing ventilation system. The first term is air change per hour, or sometimes we call it ACH in short. The meaning of this is very straightforward. It is the ratio of the volume of outdoor air flowing into a given space in an hour divided by the volume of that space. The second term is ventilation flow rate, or in short, ventilation rate. It is generally expressed in liters per second. You will see this term commonly used in statutory regulations, codes, and engineering standards. Usually, the requirements state the minimum ventilation rate per person. So for places where the number of persons may vary from time to time, the air change per hour would change due to its occupancy status. The formula shown on the slide simply defines the relationship between the air change per hour and the ventilation rate. It is simply the ventilation rate multiplied by the time and divided by the room volume. Next are the terms negative pressure differential and airflow direction. These terms are commonly used for healthcare premises, isolation facilities in particular, to indicate pressure inside the room with respect to its surroundings. Smoke tests are generally carried out to verify whether the ventilation system has achieved its desired flow direction. Most physicians are familiar with the terms clean zone and dirty zone, as the setup of the clinical facilities requires looking into the workflow to avoid cross-contamination. In ventilation, we want to design a system that draws clean air into dirty zones and extract the dirty air via a filter to the ambient environment. We then come to the last term, which is filtering efficiency. The minimum efficiency reporting value, or sometimes referred to as the MERV rating, and high efficiency particular air filter rating are the commonly used measurement scale to specify the effectiveness of air filters. The MERV rating is the American standard designed by the American Society of Heating, Refrigeration, and Air Conditioning Engineers, or in short, ASHRAE. Its value ranges from 1 to 16, with higher value meaning higher filter efficiency. In Hong Kong, we usually use the HEPA rating, which is an European standard. And for hospital applications, filters with HEPA grade 13 or even 14 are generally used. For ventilation using filters, designers must be aware that the fan should be compatible for use with MERV or HEPA filter, since the fan must be capable of generating sufficient power to move air through the filter. This also means higher energy cost to operate such fans. In a typical ventilation system, fresh air is drawn from outdoor by either an air handling unit or fan coil units. The return air mixed with the fresh air is then conditioned to the desired temperature and relative humidity and supplied to the occupied space. At the bottom of the slide are two equations showing the definition of two different air changes per hour, namely the total air change and the fresh air change. It is important not to mix up the ACH of fresh air and total ACH of the room, which have different meanings and requirements in the regulations and standards. While we are at this slide, I would also like to bring up a very simple concept about positive and negative pressure environment. To achieve a negative pressure in occupied space, the exhaust air fan should be designed and operated to have a ventilation flow rate greater than that of the fresh air intake. And for positive pressure, it is just the vice versa. In this next section, I will briefly go through the relevant statutory requirements and guidelines on ventilation. In Hong Kong, there are three main regulations stipulating the statutory requirements on ventilation systems in buildings. The building planning regulations specifies the requirements on providing adequate ventilation for building intended to be used as an office or for habitation. The Public Health and Municipal Services Ordinance specifies 6 classes of premises and their minimum fresh air requirement per person occupying the premise. And the Labor Department also issued a guidance note on ventilation and maintenance of ventilation systems, which specifies the fresh air supply rate for general work activities in an air-conditioned areas. For example, The building ordinance promotes the use of natural ventilation as it sets minimum requirements of openable windows. However, it's not often that we have openable windows in commercial buildings in Hong Kong. Even if it does have such provision, its operation is largely dependent on occupants' behavior, especially in the cold season. As such, the building planning regulation states that if you cannot satisfy the openable windows requirement, then a mechanical means of ventilation, which shall be capable of supplying fresh air at a rate of not less than 5 ACH, is required for office. It is important to note that the 5 ACH of fresh air does not necessarily mean that the entire room has an ACH of 5. Under the Public Health Municipal Services Ordinance, the fresh air requirement of 6 classes of scheduled premises are defined by the amount of fresh air per hour per person, which was just a question asked by Dr. Jane in the last presentation, and who may be accommodated by the premises. The guidance notes on ventilation and maintenance of ventilation systems issued by the Labour Department also specifies fresh air supply rate for general work activities in air-conditioned areas. For places such as offices, schools, conference rooms, canteens, where the number of persons present is normally constant or nearly constant, a minimum fresh air supply rate in terms of the number of persons is specified. But for places such as shops, supermarkets, restaurants, where the number of persons may vary from time to time, the minimum fresh air supply rate in terms of total floor area of that workspace is specified instead. So to allow you to have a feeling on what these numbers represent, let me work out a very simple calculation. Let's take a conference room of 20 square feet with 10 people occupying as an example. The 200 square feet with a simple calculation or simple conversion works out to be approximately 18.6 square meter. Assuming a normal office with a ceiling height of 2.5 meter, the volume of the occupied space is approximately 46.5 meter cube. With 10 people in the conference room, the minimum fresh air supply rate, in accordance to the aforesaid regulations, is to be 10 cubic meter per minute. That is equivalent to 600 cubic meter per hour. So with a room of 46.5 cubic meter and use this formula, the minimum fresh air change rate per hour is approximately 12.9 ACH. This 12.9 ACH is in fact a very good ventilation. As you will later see that the international standards specified a minimum ACH of 12 for the hospital's airborne isolation wards. Now we turn to international standards and guidelines issued by the recognized authorities. There is no better place to start with the World Health Organization, WHO. We often make reference to guidelines published by WHO. In fact, WHO also issues many practical advices for the public to better protect ourselves against the disease. The topic of my presentation is what role does ventilation play? I think the following figures extracted from the WHO guidelines answers pretty much the question. The table you now see on the slide illustrates the calculated pollutant concentration decay with different ventilation rates in fully mixed isolation rooms. It is assuming that the pollutant concentration in outdoor air is 0, and there is no source in the enclosed space according to the simple concentration decay equation. So what this means is that we assume a room is initially full of pollutants. As you will see, the percentage of pollutants at time 0 is 100%, and with the different ventilation rates stated in ACH, the pollutants are being extracted from the room. The table shows that after 10 minutes, with an ACH of 6, around 60% of the pollutants are removed from the given space. As the ACH goes up, a much more significant reduction of pollutants is observed. From a removal of around 87% with an ACH of 12, up to a reduction of around 98% with an ACH of 24 within the 10 minutes interval. And within the same WHO guideline, there is a table showing the infection risk with 15 minutes exposure and different ventilation rates. The figures were based on the use of mathematical modeling of infection risk to estimate the effect of ventilation rate on infection probability for known airborne diseases. It is worth noting that the equation was developed for predicting the probability of airborne disease transmission. For COVID-19, where a majority of transmission is based on close contacts, the figures may not represent the risk of infecting COVID-19, but it does give us a very good representation of how the risk factors reduces with increasing ventilation rates. Having seen the figures above, I think you will have a pretty good idea what role ventilation plays in tackling the disease. For engineers, we regularly look at design guidelines issued by international standards bodies. One of the more renowned standard bodies is the American Society of Heating, Refrigerating, and Air Conditioning Engineers, in short, ASHRAE. In the section on common terminologies above, you may recall that the MERV rating on filtering efficiency was a standard developed by ASHRAE. Since most of us today are health professionals, I would like to share with you two standards issued by ASHRAE. The first one, which is on the left, is standard 62.1 ventilation for acceptable indoor air quality, with its latest version issued in 2019. This is a standard that addresses procedure of testing indoor air quality, procedure for measuring ventilation rates for mechanical and natural ventilations. The second standard is ASHRAE 170 on ventilation of healthcare facilities, with its latest version issued in 2017. This is a standard often referred to by engineering consultants on the design of hospitals and clinics in Hong Kong. It states the different ventilation requirements for commonly found occupational areas at healthcare facilities. For different types of isolation wards at hospital, it has its particular set of requirements. Now, this figure shows a typical design of a negative pressure airborne isolation room at hospitals. When you enter the isolation room from the corridor, which we usually call it a clean zone, you will pass through the anteroom. The doors of the anteroom are interlocked to ensure the air from the patient's room will not escape directly to the corridor. Exhaust fans are installed inside the patient room and bathroom. The designed airflow direction of a negative pressure isolation ward is from corridor to anteroom to patient rooms and bathroom. The air then passes through a filter and extracted to outdoor. In order to achieve the desired airflow direction, we need to create a negative pressure environment by having fans which extracts air at a higher flow rate than that of the supply air. In the ASHRAE standards, the design of the isolation rooms should be able to achieve the following requirements. They should have at least 12 fresh air ACH. The pressure differential between the corridor and the isolation room should be at least negative 2.5 Pascal. The standards also requires a filtering efficiency of 14 MERV rating or above. And for most isolation wards in public hospitals in Hong Kong, HEPA filters of grade 13, which has a higher filtering efficiency than the MERV 14 rating, are used at the exhaust. In the early stage of the COVID-19 outbreak of Hong Kong, the hospital authority wishes to enhance the handling capacity of COVID-19 patients in the public hospitals. So they came up with an idea to convert some of the general wards to a so-called second-tier isolation ward. The design of the second-tier isolation ward is simply changing the airflow pattern of the ward. Fresh air flowing into the ward through air handling units and will float into the patient cubicles. The dirty air in the patient cubicle will be extracted out from the patient cubicle to outdoor through HEPA purification units. In a conventional arrangement, the conversion of such ward requires a substantial modification of the ventilation system in the general ward, by changing its configuration from a positive pressure arrangement to a negative pressure arrangement. However, such modification requires months of completion and was technically infeasible to complete within a very short period of time. Also, there was a need to revert the operation of the ward back to a general ward for future use. With the technical knowledge and experience in operating isolation wards and making reference to the designs of isolation room, The hospital authority and EMSD jointly developed a mobile air purification unit with HEPA filter for this purpose. This photo shows a typical configuration of a second-tier isolation ward with two sets of mobile HEPA purification unit installed. The two units were installed for backup purpose. That is, one unit will maintain the operation in case another one is broken down. Together with the necessary commissioning of the original ventilation system in the ward, the mobile HEPA purification unit was designed to allow the general wards to achieve an ACH greater than 12 and to maintain a pressure differential of negative 2.5 Pascal, which is equivalent to a standard airborne infection isolation ward. On-site testing were carried out at the trial hospitals, and you will see from pictures that smoke tests were carried out to verify the airflow direction. Measurement of room pressure differential was conducted. Also, the ventilation flow rate was measured to verify that the desired ACH was achieved. Upon verification of the results, the mobile HEPA purification unit went into mass production and had successfully assisted HA to increase the number of isolation facilities and hence the handling capacity for the COVID-19 patients. Ever since its first deployment, the second generation of the mobile HEPA purification unit has been integrated with NB-IoT capabilities to receive signals on its operational status, allowing operator to easily monitor its proper operation and carry out any necessary maintenance such as filter replacement. The conversion of general water was only able to solve a short-term needs. And with the sustained development of the COVID-19 pandemic, there was a need for a mid to long-term plan to increase the number of beds. In this respect, the government of the Hong Kong SAR and the hospital authority has set up a community treatment facility at Asia World Expo exhibition halls to house patients with mild symptoms. In parallel, Chinese central government also provided great support to Hong Kong in the expansion of the treatment facilities at Asia World Expo with an additional capacity of around 1,000 beds in Hall 8 to Hall 11 of the AWE. There were multiple challenges in converting Asia World Expo's hall into community treatment facilities. One of the challenges was to modify the ventilation system of an exhibition hall to meet the ACH and the negative pressure requirements for treatment facility purpose, for which we have also made use of the aforesaid mobile HEPA purification units. Similar modification was also implemented in various sports centers, which were used for setting up the 5I laboratory and the specimen collection center for the universal community testing program in September. The ventilation system of these sports centers were maintained by EMSD, and we had immediately changed its ventilation mode in order to enhance the ventilation system for the purpose. As we all know, Hong Kong is an international hub with many travelers coming in and out on a regular basis. Although the number has significantly decreased since the time of the pandemic, there are still a number of travelers that would carry on with business in Hong Kong. With the mandatory quarantine measures in place, the government looked into the possibility of using hotels as a place for the holding of quarantine facilities. EMSD was tasked to review the ventilation setup at various hotels and to provide advices from ventilation perspective. In order to lower the risk of the hotel staff being infected by gas quarantined inside guest rooms, an airflow from corridor to guest room was required. Sampling tests were carried out on site to check the airflow pattern. Now this video shows smoke tests being carried at the hotel. So let's look at the video first. So here is a hotel guest room. And we conduct smoke tests in the toilet.
好，試下抽煙先。OK。
抽氣正常。
抽氣正常。OK。
As you can see from the video, proper airflow pattern from bathroom to the exhaust, from guest room to the bathroom, as well as from the corridor to the guest room, was tested and observed in hotels in this case.
Guest room。
好，唔該晒。
Apart from the airflow pattern, We will also check the distances between fresh air intake and sources of pollutants, such as exhaust air outlet and drainage fan pipe outlets to ensure no foul air will be short-circuited or infiltrated into fresh air intakes. Although there is no recognized international standard or focus on distance for hotel as inbound traveler holding facilities, we made reference to the requirement of 25 feet, which is approximately 7.5 meters, stipulated in the ASHRAE standard, as well as the CDC's guidelines for environmental infection control in healthcare facilities. Impact assessment to buildings in the vicinity of the hotel were also reviewed. For instance, were the exhaust air outlets of the hotel close to air intake or openings of adjacent buildings? Whether the exhaust air from the hotel was discharged to the pedestrian path? These questions were taken into consideration in determining whether a hotel could be used as a quarantine facility. In July of this year, there was an outbreak of COVID-19 at elderly homes. Both the elderly and caretakers staying and working at the places were diagnosed of the disease. This led to a prompt investigation into the cause of the outbreak. EMSD was tasked to assist in reviewing the ventilation system of the dormitories. Reference was made to statutory requirements and international standards to formulate a set of guiding principles for checking the ventilation system as shown on the screen. It includes the fresh air supply rate at a minimum of 10 liters per second per person, distancing requirements between fresh air intake and sources of contamination, the airflow pattern from clean to dirty, and the minimum ACH for various different areas in the elderly home. And I'm going to share with you some observations in two different cases. In case one, there was adequate fresh air being supplied to the dormitory. However, the distance between the exhaust pipe duct and the fresh air pipe duct was found to be approximately 4 meters only, which is less than the 7.5 meters requirement, and there may be a possibility of short circuit between the ductworks. Also, the mechanical air intake rate with approximately 105 liters per second was found to be much less than the mechanical exhaust with approximately 260 liters per second. This essentially created a negative pressure environment inside the dormitory. Fresh air was being pulled in from a dirty light well where it was suspected to have drainage leakage. As a result, a foul smell was observed inside the dormitory. In addition, only fresh air supply with no exhaust ductwork was observed in the designated isolation rooms, which is right here at the bottom left. This created a positive pressure environment inside the isolation room. And to sum up, it was observed that there was initial design flaw on the ventilation system. Also, proper maintenance of ventilation system had not been carried out. All these may contribute to the rapid outbreak of the COVID-19 cases in this elderly home. In the second case, there was no mechanical air intake to the dormitory, but only mechanical exhaust ductwork. The design relies on fresh air being pulled into the dormitory via building gaps and openable windows. However, most of the windows were found closed and fresh air could hardly be pulled in. It was also noted that the toilet exhaust passed through the exhaust opening in the bedroom, which is right here, making a possible mix between toilet exhaust and bedroom as shown in the figure. In both cases, recommendations on rectification of the ventilation system were offered to the owner of the elderly homes to improve their ventilation systems. Apart from the elderly centers, there were also a small cluster of infection cases from public markets and fitness centers. Our engineers were once again on site to review the ventilation performance. For fitness centers, it was observed that fresh air was mixed with recirculation air, which greatly reduced the fresh air intake capacity, resulting in high CO2 concentration within parts of the premises. Also, some air intakes and outlets were found close to each other, and short circuit of air was observed. For the problem on fresh air intake, simply reducing the air damper on the recirculation air ductwork could solve the problem. All in all, proper ventilation equipment were installed at the fitness center. Only slight adjustment on the setting will be able to create an environment that is less vulnerable to the spread of disease. For the public markets, There was no evidence showing that the infection was caused by the ventilation. Meanwhile, we have installed additional mechanical air movement equipment in the public markets with a view to enhancing its ventilation rate so as to reduce the risk of infection due to the insufficient ventilation inside the very crowded public market area. One might ask, how do I go about to improve my ventilation if I'm not an engineer? So my advice is first, appoint a ventilation specialist to review your ventilation design and settings. As in the case of the fitness center I just mentioned, proper equipment were installed. However, the settings might be off. For other cases, there might be a need to install additional fans and equipment in order to achieve the desired airflow results. But this is not the end of the equation. What most people forget about is that proper ventilation system requires proper maintenance. For instance, were the filters regularly cleaned or replaced? Were the fans operating at its designed mode? Are your equipment near its serviceable life and required replacement? All these facility management issues are required to be dealt with properly in order to maintain an operating and proper ventilation system. Since the outbreak of the COVID-19, many of our daily routines have been disrupted and human behavior has changed. For instance, we order more takeout foods than we used to. Many of us use online shopping instead of going to groceries to buy our daily needs. We use video conferencing like today, more than we have ever used in our pre-pandemic times. Also, we are much more aware of the need for good ventilation than we used to. Staying indoor does not necessarily mean that it is safe unless you have a properly designed ventilation system. With problems come opportunities. Money we usually spend on things that we can see to improve the appearance. Less is spent on ventilation systems, which are less noticeable. There is no doubt that the general public is more aware of the need for proper ventilation, as improper ones might result in businesses being shut down and even people getting infected and killed. So spend the efforts now to improve your ventilation. And this is the end of my presentation. Thank you.